talking about project 4, and hopefully with this video it can bring you up to speed with this project. Let's get started. So there are a couple of things you should be aware of when you're doing this project, because we're dealing with file system in this project. First of all, like, what is a file system, right? So file system is just a storage place for your files to be stored, and then you can traverse the structure of the file system, the directory, subdirectory, and so on, right? So in a PintOS, how do we interact with a file system? Well, here there is this variable called fs device, a file system device, right? So this represents the file system in PintOS. You can of course look into how this variable is initialized and used and so on, but at this point you should just know that if you want to interact with a file system, this is a variable, and a file system in PintOS is just an array of sectors, right? As what I drew here. It's a big array, and each entry is what we call a sector. So you can simply treat this fs device as an array, like a very long array of sectors. And if you want to use a particular sector, then as long as you know the sector number or the sector index, right, you'll be able to access it. Okay, so other things you should be aware of is the inode data structure and also inode disk, right? Let's talk about inode first. So what is inode? Well, this is an in-memory data structure. So behind every single file, there is an inode. What do I mean by that? If you look at this file.c, there is this file struct, right? And within this struct, the important attribute is this inode pointer. So we know behind every file, we have an inode that's pointing to it, right? And within this inode structure, you should pay attention to the sector number. I will explain more in detail later on in this video, but you just need to know this variable, this member variable exists. And also another one that's pretty important is this data variable, right? That's an inode content. It's a type of inode disk, which is this data structure that we'll be looking at. So inode disk, you can think of this as it says it's an inode content, right? So you can think of this as like the file content, right? Like I said, file has an inode pointer pointing to it, and then through this inode pointer, you can get to the data portion of the file. And then once you are in inode disk, you know the start and length. So what do I mean by this? For example, this is the first data sector, right? So again, using our file device sectors, right? For example, a particular file, let's say file A, the starting the start sector number is, let's say 4, right? Then we'll be looking at or let me use 3 actually, right? Then we'll be looking at this entry, right? So we know the file kind of starts from here and going onwards, right? And then we know the length of the file. So the file size in bytes, right? Because each sector is 512 bytes, right? As this macro defined, 512 bytes. So let's say, life is not always perfect, right? So let's say we have a file that is 513 bytes, right? So this is 1 byte bigger than a sector, right? So 512 is 1 sector. 1 sector plus 1 byte, right? So using this example, we know this file will take sector number 3, that's for sure, right? That's for this one sector, right? And then for this one actual byte, it will take 1 byte from from this sector, right? So in total, the file will take this much of the space, right? Okay. So yeah, it seems like a pretty straightforward method to store files, right? But the problem with this is external fragmentation. What do I mean by that? Here, look at this graph that I drew. Again, this is, so they're the same thing, right? I just drew this graph by hand. And let's say file A starts from sector number 1 and it spans to sector number 2, right? It may take half of the index 2 sector. It may take the entire sector number 2, right? It doesn't matter. Right now I just want to show you this file A takes 2 sectors, right? And B takes another 3 sectors, right? Okay, you might ask me, okay, why B is not taking sectors right after 2, right? Why B is not this 3 sectors instead? Well, maybe before you have a file C, right? File C kind of takes some sector, taking 1 sector, and then later on we delete file C, right? So this sector becomes available, right? But yeah, for whatever the reason is, let's say B right now just takes sector 4, 5, 6. Okay, so now we have a problem, external fragmentation, right? Because if we want to create another file, let's say file D, and file D will take 3 sectors, right? Although we do have 3 sectors, this one, and this one, we do have 3 free sectors. However, with the current implementation, we simply just cannot accomplish this task, right? Because these 3 sectors, they're not consecutive. Therefore, no matter which one you set as a start sector, you cannot have 3 consecutive sectors for this file D, right? So that's what we call external fragmentation. That's a problem. So in this project, you will be modifying this data structure, right? So a better way to or the solution to tackle this external fragmentation is, in this data structure, if you have pointers, right? Pointers pointing to where this file is stored, right? So you might have a pointer pointing to the sector number 0, a pointer pointing to the sector number 3, another pointer pointing to the sector number 7, right? So within the inode disk, all the sectors that are used by this file, then they don't have to be consecutive, and you just solve the problem of external fragmentation, right? Yeah, so here I just wanna kind of get your attention that this is where you kind of make that modification. However, it will be a lot more complicated than just writing down the index, right? So in this video, I'm not gonna show you how we'll be doing that. That's your job. You need to figure it out. Maybe later on in this project, I will offer more help. But at this point, you should realize this is a problem, and if you want to change it, this is where you change it, right? Okay. Let me clean some of the drawing, and then I will. Okay, let me leave this part. So clean this part of the drawing. Okay, and then now I will use an example to show you how do we use a file system, right? So you have been using file system for the previous projects already, right? But the problem with the current file system implementation is very limited, right? The functionality is very limited, and in this project, you do want to extend other features for the file system to make it more similar to the file system that we use on a daily basis, like in Windows or Mac, right? I will be using this file system open handler. This is in the system called .c, which you have implemented already. Of course, here you see it's a very simplified version. Yours is like your system open handler definitely has a lot more complicated logic than this one. But if you have the correct implementation, most likely you will have already used this function inside system open handler, right? File system open, right? So let's take a look at this function. All right. Okay, so we pass in the file name that we want to open, right? And then we call this file sys open. Now we have the name. The first thing we want to do is we want to open the root directory, right? As the name itself, it's pretty self-explanatory. Directory open root. So within this function, we'll be calling directory open on the return value of inode open. So we'll first look at this inode open. The inode open passing this macro defined as 1. So that's a sector number, right? That's the parameter. So right now, it opens a root directory, right? So we know the root directory. So in PintOS, a file and a directory, they are really no difference, right? Probably the only difference is, file just contain bunch of data, right? But for directory, its data is kind of special, right? Its data is not the text file and so on, right? Its data is probably other files, right? Maybe it, like what I drew here, right? You have a directory A. Directory A may have its own substructure of another directory and maybe another file, another directory and so on, right? But in essence, they're really no different, right? From the point of view of the file system, they're just like a unit of data, right? Or a bundle of data. Yeah, so let me clear this. Let's continue. Here, this is what we define as 1, right? So we know the root directory sector. Remember, in the inode structure, there is a sector, right? So we define this always to be 1 for the root directory. That's by definition, right? We define this inode structure for the root directory is always stored at sector number 1. So no, like every time when we create this file system, by default it's always gonna be this location, right? Okay, so let's take a look at this inode open. We pass in a sector number, right? And here we just do a simple traversal of all the open inodes, right? If you look at this, this is a list of open inodes. So if we find an inode, if it's sector number again, right? This sector number is what we passed in, which is 1. If this is true, we just reopen the inode number, right? The inode reopen basically just increment the open count, right? Increment the open count here. This is the first time we try to open the root directory, right? So of course it shouldn't be in the open inode list. Therefore, we'll finish this for loop and continue on. We malloc inode, and then we just set its member variable as what we pass in the sector is 1, and then the open count is 1, right? It's the first time we open it, and so on. And then block read, right? Block read, if we read what it does is it's reading a certain sector from block into buffer, right? Since this sector is what we set here is 1, right? So we basically just read the data at this location, sector number 1, from the file system device, from the big array into buffers, right? So into this inode data, right? We read into this variable. So that's the inode disk, right? Okay, so now at this point, right, because we read the data into the inode data, so we know, right, with the content of the root directory, we know the content of it, we know the start, we know the length. So if we want to find what files or directories are available in the root directory, now we know where the data is stored, right? Because we know the start, we know the length, so we can literally use these two variables to locate where the actual content of the directory is, right? For example, it's in this sector, right? Okay, and then let me go one step back. So now we have we return the inode pointer, right? And then we call dir open on this because it's a directory, right? It's a root directory. Okay, and in this function, it's pretty simple. We just calloc a directory pointer and then set the inode to be, you know, the inode that we pass in, and then return the directory pointer. Right. So now we have the directory pointer, and you know, it should be null, right? If everything is successful. So we will just look up. So in this current directory, in this root directory, we want to look up a file whose name is name, right? And then we pass in this inode being null first. Okay, so we look up. Here again, we call this lookup function. So this lookup function, let's first read what it does, right? Search this dir in this current directory. We search for a file with a given name, right? If we find it, we return true, and then we set this directory entry pointer to that directory entry, and so on. So okay, so what it does is basically, you know, here we have a for loop, right? So inode read resides bytes from inode into buffer, starting at the position offset, right? So basically what this does is every time we try to read from the inode, remember this inode, we set it before, right? We set it before to be we set it to be the inode of this root directory, right? Okay, and then we look up. So for this this inode, this inode is pointing to this, right? This root directory inode. And each time we read the size of E. So E is directory entry, right? Because root, this one root is a directory. So within it, you know, either if it's a file or it's another directory, it's just another entry, right? So this is entry, you know, entry 0 and entry 1, entry n, right? So each time we try to read one entry, and then we compare if this entry's name is a name that I'm searching for, right? So if they're the same, then I just set this this EP to this entry, right? So this EP is what we passed in from the last function call, and we pass in null, right? They will pass in E. Okay, so now if we find it, meaning we find the file, right? Now we just so for example, we find this file 1, if this file is what we want to find, right? And then we find it. Now we just need to open the this we just need to inode open the we just need to open we just need to read inode from sector, right, and return this inode inode pointer, right? Because we already find this entry, and within this entry, this is a directory entry. Within this entry, we also have an inode sector, right? This sector number, right? So now with this, it's basically the same as finding where the root is stored and then open it, right? Same thing. Now we know the sector number for this file 1. We just open this one, right? We find a sector number. If it's first time, we create a new one. We already traversed this function already, right? And then we return this inode. So now we have another inode. We have the inode for this file 1, right? Inode. Yeah. That's pretty good. And then let me go back. Okay, so yeah, so we open this inode, and the inode, of course, this pointer is not null, so return true. We find this file, right? Okay, so after we find this file, and we have this inode, we give the value for this inode, which is null when we pass in. Now this inode is has a value, right? And we try to open this file, right? The file being pointed by this inode pointer. And yeah, in this, again, we traverse this file already. So once this is done, we return the file pointer. And we return the file pointer on this level as well. And then we get the file pointer, right? And later on, you can continue with the the logic of the open system open handler, right? But in this project, another thing you need to do is for all the previous projects, you're only dealing with files, right? You're not really creating subdirectories and so on. But this one, once you get the file pointer, remember I said in PintOS, at least from the perspective of the file system, there is really no difference between a file and a directory, right? So this one can return you a file pointer, right? Maybe a pointer to this file, file 1, if that's a file you want to open, or maybe you actually want to open directory A, right? So if you pass in the name, something like maybe like this, right? Folder A, folder B, and then the last folder, right? So then what this returns you is the file pointer to a folder, right? To a directory. So it might return you this. So of course you have to deal with if this is a file pointer, then because you want to open it, of course later on you still have to deal with the logic. How do you open this file? How do you open this directory, right? But as we see in this function, it's not very difficult, right? Because if it's a directory, then within this directory.c, you do have functions that you can use to simply open the directory, right? Directory create open, right? Okay. All right. So I hope up until this point everything is clear, and let me see. What's the next thing I want to cover? Okay. So far everything is good, right? But there is a part of the logic in the workflow that we just discussed about is quite important to us. So let me go back to the logic we're traversing, we're following. So we first get into this file sysopen function, right? And then once we get the directory pointer of our root directory, and then we will try to look up the file within this directory, right? And then we call lookup function, and within this we try to read the entry under the root directory and compare if they have the same name, right? And then if they do have, you just give the value to that. You just give the value of the entry pointer, assign it to this EP, and then you return it, right? But we didn't actually look at how this function is implemented, right? So now I think we can look into what this function does. So first of all, here what we're doing is we try to read the directory entry one by one and compare the name, right? Okay, let's see what it says here. Read size byte from inode into buffer, right? So read from inode into buffer, starting at position offset. Okay, starting position offset of the inode, right? We have a start, we have a length. We start from the offset, and then we try to read size byte of data into buffer. Okay, so of course we want to only consider size bigger than 0, right? Otherwise, if it's less than 0, it's an error, right? If it's equal to if it's equal to 0, then we don't actually need to read anything. So here, when we get in, we first use this function to convert the byte to sector, right? Because we're trying to read from the offset of the inode. So we need to know this offset is at what sector number, right? So what do I mean by this? Okay, so here, right? Let's say this start. Let's say the start is 2, all right? Is 2, and then the offset. The offset might be smaller than maybe smaller than 512. Then offset will be somewhere in sector A, right? Or this sector number 2. So now we know the sector index is again the second one. But if the offset is pretty far away, maybe the offset is something like 600, and if the length is like 700, something like that, right? Then we'll be looking at the second sector, because the first sector only covers the first 512 bytes, right? So because we're looking at offset 600, then that will be somewhere in the next sector. Remember, they're consecutive, right? So it will be in the sector number 3. And that's what this function does. So we basically find which sector we want to read data from, right? So if you look into the implementation, this is exactly what I just described, right? From the start to divided by the sector size, we know from which sector we'll be reading data from. Okay, and then we need to, now we know which sector we want to read data from. Let's just use one example. We try to read data from this sector, okay, from this sector. So from the second sector, or the second sector from the starting location. But if we look at the overall index, it's index 3, right? And we offset divide or modulo by 512. So what that gives us is the starting position of the sector to to read from, right? Because we're reading from the second sector, then we modulo 512, we get the sector offset, right? So instead of being 600, so now it should be 600 minus 512, right? That's the offset of this sector. So that will be like 88, right? Okay, and then we know the inode length, it's in this variable, right? We know the inode length, we minus the offset, we know how much space is left, right, from this offset, right? Because in total the inode is length 700. We're reading from the position of 600. We're left with 100 byte of data to read, right? Once we read this 100 byte of data, we're done. There's nothing more to read, right? That's the end of the file. So that's this variable. And then the block sector size minus sector offset. So this is sector left, right? So for example, here this is 512, right? And the sector offset is what we calculated, 88. So this value will be 512 minus 88, and this one is 700 as we defined here, length, right? 700 minus 600, right? So this is 100, and this is 512 minus 88. So 424, okay, right? And we want to take the minimum of these two, right? That's the minimum. The minimum of this two is the actual. So we want to take the minimum of these two, and then from the next line of code, if the size is less than this, then we would read size. Else we read min left. Okay. We first know the min left is this. We take min of this two, so that'll be 100. And then the size is we read size back from inode into buffer, starting at position offset. Number of bytes. So here it's the number of bytes to actually read from this sector, right? Why? Because if we only have 100 byte of data to read until we reach the end of this file, right? If our size is less than this, that means we don't actually want to read until the end of the file. Otherwise, we just read whatever is left, right? So this is, as it says, the number of bytes to actually copy out or read from this sector, right? So this is the number of bytes to read from current sector, right? And yeah, of course, if it's less or equal to 0, we break. And here, if the sector offset, right, here, if the sector offset is 0 and the chuck size is 512, that means we want to read the entire sector out, right? Maybe this example is not very good. Let me kind of redraw this example. Right. So here, this is a plus 1. This is a plus 2. Right. So because we're reading this file one sector a time, right? That's why we have this while loop. Before we read the last sector, right, the previous sector, we might need to read the entire sector, right? That's why if the offset is 0 and the chuck size is 512, that means we need to read the entire sector, right? If we do read the entire sector into the buffer, well, then that's pretty easy, right? Because we know the sector number. Here it's number 3, and we need to read it into the buffer. So that's pretty straightforward. We directly read from the file system into our buffer, right? From which sector index, we already calculated, right? So from this sector index of the file system, we read it into the buffer. Well, if this is not true, that means we're reading part of the data, right? For example, this is the last sector, and we're only reading this much data out. Well, in that case, we want to create a bounce buffer. So this is something, if you read from the handout, you'll notice this is what they call a bounce buffer, right? So the first time, of course, the bounce buffer will be null. That's why we need to malloc. But then the next time when we run this while loop, it won't be null anymore, right? Because we already created, we already allocated the memory for this buffer. So first we create this buffer. And once we create this buffer, we read from the file system at this sector index, right? Now, because we're dealing with this one, so we'll be reading from sector number 4 of the file system into this bounce buffer first, right? So we read into like a bounce buffer. So we read into a bounce buffer. Right? So we read into the bounce buffer first. And then okay, again, this example is not very good. Because the reason why we want to have a bounce buffer is in a situation where we're not reading from the very beginning, right? So maybe we only want to read this part of the sector, right? I know the example I'm giving keeps changing, but like I don't think it's difficult to see why I changed the example, right? Because here we want to, here, because I don't want to read out the entire sector into my buffer. I only want to read this part of the sector, right, into my buffer. That's why I can't, because every time when you read from this file system, you read the entire sector out, right? But if you read the entire sector out directly into our buffer, right? So say this is our buffer. This is buffer. This is the buffer that's being passed in, and this is this bounce buffer. So bounce, right? So if we read the entire sector into our buffer, right, this might overwrite some important data that we have, right? Maybe here we have some data that's important to us, but if we read the entire sector out, it will just rewrite everything, right? Instead, we don't want to do that. We only want to fill this part of the sector, the buffer. That's why we first read the sector out into a bounce buffer, so it's being filled, right? And then we only copy from the offset of this bounce buffer into the offset is into some specific location of the buffer. and we copy this chunk size of data, right? So now we can selectively only copy this part of the data into our buffer. So that's why we need a bounce buffer, right? And your task is to remove this bounce buffer. And now the reason why you need a bounce buffer is because like I said, every time when you try to read from the file system, right, you always have to read the entire sector out. So in this case, if you do want to read the sector from a certain offset, you need to put it into a buffer, this bounce buffer, right, this bounce. And then you can selectively to choose which portion of the bounce you read the data from. That's a problem, right? So in this project, you want to create something called a buffer cache, right? So imagine when we try to read from this sector number 4. So how do we tackle this problem? Well, if the data of this sector is in our memory already, right? If it's in memory, that means it's already in some sort of in-memory buffer, in memory. If it's in memory, then we want to only fill this part of our buffer. That'll be easy, right? Because this is in memory already. So think of it as an array, right? Then you can call this function to selectively only select this part of the in-memory buffer cache and put the data into our destination buffer, right? So in other words, instead of allocating this bounce buffer every single time, you want to have sort of like a permanent bounce buffer always in memory. And what we call for this permanent bounce buffer is buffer cache, right? And how do you kind of keep this buffer cache always in memory? Well, when you start the entire system, right? If you kind of allocate enough space in memory, then if we read the sector that we want to read data from into this in-memory data structure at some point, and then when we later on need to use the data from this sector instead of reading it from the file system, we can simply read it from this in-memory data structure that we created when the system is boosted up, right? So this part is what we call a buffer cache, and that's what you need to do. In this is where you will be writing your buffer cache, and this is inode read, and you also have inode write, right? So here again, see there's a bounce buffer, right? So you also want to replace this part as well. In the handout, there are also something that we mentioned, read ahead and write behind. So read ahead and write behind. Read ahead, write behind. Right? So what does this mean? Well, the entire reason why we want to have this kind of in-memory buffer cache is when we need to read data from the file system, it's already in memory, right? So we don't need to actually interact with the file system which is an I/O operation. That's quite expensive, right? It's taking a lot of time. Rather than doing that, it's in memory already, so I can just access that part of the memory, that part of the data in memory. That's very quick, right? But we want to do this ahead of time, right? So maybe the first time, we try to read this sector, it's not in memory because how do we know which sector we want to read data from, right? So the very first time we don't know. Then here we may invoke a I/O operation to read this sector into this data structure first, right? But the normally when we read the file, right? If we're reading this sector, very likely we'll be also reading data from the next sector, right? Because this file, right now I'm drawing them as a consecutive memory, but remember, when you replace I know, right? But remember, when you change this I know disk, they won't be consecutive anymore. But regardless, if you read, like page one of a file, most likely you will also proceed reading page 2 and page 3 and so on, right? So when you load this page 1, right? When you load this page 1 into the memory, you just kind of take a guess that you will also read, this is page 1, you also read page 2, right? So this first is an I/O operation happening at the time when you want to read it. It's very expensive, but then you might want to have a background thread, like an asynchronous thread that will secretly read the second one into memory as well, right? So this is async. So now we make this guess that if you read page 1, very likely you will read page 2. Well, if that doesn't happen, well, no problem. It's just a background thread, right? That's not really overhead for us. But if you do end up reading the second page of the file, well, now guess what? When you try to read data from the second page, it's already in memory, right? It's already in memory. It's loaded by this background thread. So we don't actually need to wait for this I/O operation. We just go and grab the data in memory, right? These are both in memory. That's what read ahead means. We are trying to read ahead next sector that the program may need data from, so that when that does happen, then because the data is already in memory, it will be very efficient, right? So now what is right behind? Well, right behind is when we write data to the file, right? When we write data to the file, instead of writing the data directly back to the file, we actually want to write the data back to the buffer cache. For example, we want to here the space is running up. We want to for example, we want to write data to this sector, right? Or you can still think of it as like a page in a text file, right? You want to write to the first page. Instead of writing it directly to the file system, again, I/O operation, very expensive, right? You firstly want to write it to the buffer cache, right? So you write data here, and then later on, not at the same time, later on, you want to write it back. Why? Because now you just write data to this buffer cache. Maybe later you want to write to it again, right? Because it's in memory. If no matter how many times you write it, it's always gonna be very fast. It's in memory, right? However, if you don't have this write behind mechanism, first time you write something to this first page, okay, fine, I/O operation, pretty expensive. Second time, when you try to write something to this page, Again, another I/O operation, also very expensive, also takes a very long time, right? So that's why if you have this write behind kind of mechanism, then if you have two writes to the same sector in a very short time window, overall it's gonna be more efficient, right? So yeah, so now I think I covered all the major topics of this project. Again, in summary, you want to work with this data structure, change the start and length, so that even if you don't have consecutive sectors, you can still create a file, right? So this is a extensible file in the documentation. Let me read it. So this is here. So this is extensible files, right here, and then you have subdirectories. So subdirectories, I think I also covered. File and directory, they're really no difference. And if in a system call handler, you might get like a file directory pointer back, right? You just need to open this file directory. So that's part of subdirectory, and also buffer cache, right? Buffer cache is what I just talked about here. Yeah, so hopefully with this video, it can bring you up to speed, and good luck with this project.